That was kind of an introduction to acids and bases. Let's talk about what's going on a more molecular perspective. I won't quiz you or test you on the names of these definitions. What I want is that you can recognize what's an acid, what's a base. So the Arrhenius definition is that an acid produces hydrogen ions in aqueous solution, and that's the definition we've been using. HCl is a molecular compound. It's covalent. It's not an ionic compound, but when you put it into water, it forms ions. So it's an acid. You put HCl into water, and it becomes ionic. It forms ions. We say it's ionized. So the HCl separates into hydrogen ions and chloride ions. That meets the definition of an Arrhenius acid. Hydrogen ions are highly reactive. Let's think about what a hydrogen ion is. Start with a hydrogen atom. How many protons does a hydrogen atom have? 1. How many electrons does a hydrogen atom have? This isn't a trick question. 1. Okay, so a hydrogen atom is 1 proton and 1 electron. If we get a hydrogen ion, H+, that happens by losing an electron. So what is a hydrogen ion? It's just a proton. So we basically have just a proton. There's not even any neutrons with it. It's just a proton. That is going to be extremely reactive. We're not going to find this proton just floating around in solution by itself. In this picture, it looks like there's hydrogen ions just floating around by themselves, right? That's not going to happen. Hydrogen is a little guy in the element family, and the hydrogen ion is even smaller. It's equivalent of like a newborn baby. You see newborn babies hanging out on the sidewalk by themselves? No, you shouldn't. If you do, you should pick them up and take them to the police. So the hydrogen ion does not hang out by itself. It does not have a duet of electrons. It's not happy. It's reactive, and so it's going to look for somebody to hang out with. In aqueous solution, there's a lot of water molecules around, and so the hydrogen ion is going to come over and share one of the lone pairs on the water molecule and form this ion, which has the name hydronium. So this is a hydronium ion, H3O+. It's a water molecule with a hydrogen ion piggybacking on it, taking a ride, because it's too small to be out by itself. So what we find is that in water, hydrogen ions are always going to associate with H2O molecules, never found alone. What's potentially confusing is that we often use H plus aqueous and H3O plus aqueous interchangeably to refer to the hydronium ion. Using H plus makes the writing out the equations and everything simpler. But what you have to remember is that there's always going to be a water molecule with that. When we write molecular formulas for acids, we generally write the ionizable hydrogens first. So when an acid is put into water, it ionizes and releases hydrogen ions. So formic acid is written as HCHO2. This hydrogen is written first. This hydrogen is in here because only one of them becomes an ion. So here we have the structure of formic acid. This hydrogen stays covalently bonded to the carbon. This hydrogen becomes an ion and is going to go off and ride on a water molecule. So the molecular formula indicates the number of each type of atom. The structural formula shows us how the atoms are bonded together. So this is the structural formula, and this is the molecular formula. Any questions? So that's why some of those acids are written in kind of a funny way. There's the H first. Bases produce hydroxide ions. This is the Arrhenius definition of a base. Bases produce hydroxide ions in solution. So sodium hydroxide, that's an ionic compound. When it is put into water, it dissociates into sodium ions and hydroxide ions. There are molecular compounds such as methanol that from their formulas look like they would be bases because, oh, that's got an OH in it. but it's a covalent molecular compound. It doesn't form ions. So the bases are the metal hydroxides, the ionic hydroxides. When we have hydrogen ion from an acid and hydroxide ion from a base getting together, they form a water molecule. So the acid neutralizes the base and forms water. That's using the Arrhenius definition. But the Arrhenius definition does not explain why some substances act as bases even though they don't have OH- in them at all. And ammonia is an example of that. The Arrhenius definition also doesn't work with non-aqueous solvents. So you get into organic chemistry, and they do a lot of stuff with non-aqueous solvents, and then the Arrhenius definition doesn't work anymore. So we have the Brønsted-Lowry definition. This identifies an acid as a proton donor. A proton is a hydrogen ion. So an acid will donate a proton, will donate a hydrogen ion. A base is a proton acceptor. It's something that will accept a proton. So this definition explains a lot more things. And it focuses on the transfer of hydrogen ions. This is going to define the same things as acids as the Arrhenius definition did. It's just going to expand the definition of bases. So HCl, when you put HCl into water, it donates its proton, its hydrogen ion, to the water, giving us that hydronium ion and a chloride ion. So it's a proton donor. It's a hydrogen ion donor. So this is donating the hydrogen ion. Who's accepting the hydrogen ion? The water, H2O. So that makes H2O a base in this situation because it's accepting. So I think of the base as like a babysitter. The hydrogen ion is the baby. And so here's hydrogen ion with its parent. And they're going to pass the baby to a babysitter for a while. Base, babysitter. The babysitter takes the baby for you, right, when you need to do something else. When we look at a substance like ammonia, NH3, when we put NH3 in water, the water donates a proton to the NH3, and we get ammonium ion. So here we have ammonia and ammonium. And when water donates a proton, what's left? Hydroxide ion. Ammonia is a base. It produces hydroxide ion in solution, but we can't see that from its formula. So we're always going to have acids and bases together. If you're donating a proton, there has to be someone to accept the proton. If you're wanting to accept a proton, it has to come from someone. Okay, so we don't have hydrogen ions appearing and disappearing just like newborn babies don't appear and disappear out of nowhere. So here we have HCl and water. The acid is HCl. It's donating its proton to water, which is accepting it. The proton acceptor is the base. We end up with hydronium ion and chloride ion. Ammonia and water. Ammonia is going to accept a proton from water, becoming ammonium, and the result is hydroxide. So here we have ammonia is the base, water is the acid. Water can act as an acid or a base. And so we have a special word for that, amphoteric. A little bit like amphibian. Amphibians live on the land and on the water. Amphoteric substances can act as an acid or a base, depending on the situation. Any questions? So if we take this equation right here, so we've got ammonia plus water giving us ammonium plus hydroxide. If we write that backwards, ammonium plus hydroxide giving ammonia and water. Now who's the donor? NH4 plus is giving a hydrogen ion to hydroxide. Over here we have NH3. The difference between this and this is that it's lost a hydrogen ion. This is donating the proton, this is accepting the proton. This is the acid, this is the base. So we refer to ammonium and ammonia as a conjugate acid-base pair. One of them's an acid, the other's a base, and they are intimately related. Conjugal visits in prison, you know what that means? So this is a conjugate acid-base pair. The difference between the conjugate acid-base pair is one proton. So a conjugate acid-base pair, any two substances related to each other by the transfer of a proton. So here we have ammonia. If we add a hydrogen to it, it becomes ammonium, hydrogen ion. This is a conjugate acid-base pair. Here's water. If we remove a hydrogen ion from it, it becomes hydroxide ion. This is a conjugate acid-base pair. This is the acid, that's the base. This is the acid, that's the base. The acid is the one that has the hydrogen, and the base is the one that doesn't. Because the base is the babysitter, is waiting to hold the baby for you. So when we look at an acid-base reaction, there's going to be an acid and a base in the reactants. There's also going to be an acid and a base in the products, but those are the conjugate acid-base pair. Conjugate acid and conjugate base. So what do we need to be able to do with all of this? A question like this. In each reaction, identify the Brønsted-Lowry acid, the Brønsted-Lowry base, the conjugate acid, and the conjugate base. Okay, you can just throw the words Brønsted-Lowry out of it. Identify the acid and the base, the conjugate acid and the conjugate base. So the acid and the base are always going to be on the left side of the arrow, and the conjugates are going to be on the right side. So identify the acid and the base first. And how do you do that? Well, you look at what happens to them. When I look at this one, C5H5N, and that becomes this one, what happened to it? Did it gain a hydrogen or lose one? It gained one. So this gained, accepted a proton. Is that an acid or a base? That's the base. It's the babysitter. Oh, hey, I'll hold your baby for you. I'll take care of your hydrogen ion for you while you go on that ride at Disneyland. Whatever. They have fun too. So that's the base. This water, it went from H2O to OH minus. It donated its hydrogen ion to the base. So here, this is the acid. So we're just looking at where did the hydrogen go? The hydrogen went from this one to that one. So this is the base, it's taking it, it's accepting it. This is the acid, it's donating. Over here, we match these up with their corresponding reactants. So hopefully you can see that this one and this one are related, right? This one, this C5H5N became this. If this is a base, then this is the conjugate acid. So this is the conjugate acid. H2O and OH minus are related. This is the acid, this is the conjugate base. Any questions? Mm-hmm.
Wouldn't the H2O be associated with the OH because they were the one that lost it?
Yeah, they are associated. So the H2O is associated with the OH minus. So that tells me that this is an acid-base pair. The acid's on the left side of the arrow, the conjugate base is on the right side of the arrow. And this is a pair, a base and its conjugate acid. Any other questions? So let's look at this one. Again, looking at these two reactants, we need to identify which one's the acid and which one's the base. Well, look what happens to them. HNO3 becomes NO3. Did it lose a hydrogen or gain a hydrogen? It lost a hydrogen. So it was handing off its hydrogen ion, its proton, to somebody else. That's the acid. That's what acids do. So if this is the acid, this is the conjugate base. What's happening to water? It's gaining, right? It went from H2O to H3O plus. It accepted a proton. It's babysitting. It's the base. So this is the base. Excuse me. And what it becomes is the conjugate acid. Conjugate acid. Any questions? There will be a question like this on the fourth exam. Identify the acid, the base, the conjugate acid, the conjugate base.